All right, so going to go ahead and do our next to last part for this section, and this is resolution. Basically, what we're looking at is how far away and then how far apart objects have to be in order to be able to tell them apart. Because what happens is you get basically, like if we have an aperture, if we have and this is done for circular aperture like this thing here, but the idea is, like if you're looking at something, like even with your eye, you have two objects and the light comes in from both of them and diffracts, right? And so you end up with two diffraction patterns on top of each other where they diffract slightly, differently and everything like that. And you get these two diffraction patterns on top of each other. And so what will happen is, if the objects are far enough apart, then one of them will have a diffraction pattern peak over here and the other will be over here. So what you'll be able to tell them apart. So you have something like this for one of them, and then the other one could be, like this, like that. And you can see this would be you seeing object 1 and seeing object 2, and they would be resolved. So this would be a resolved image where the peaks weren't really overlapped. And then as the objects would get closer together or further away, so that this angle here, theta, gets smaller. So if we either move these further away, this would become a narrow angle, or if we move them closer together, this would become a narrow angle. What happens is you end up with the objects starting to overlap. So you have, the first one, and you end up getting these two things slightly overlapped, or more and more overlapped, and it goes on. And so you get a resultant, you kind of get this, follows this same thing, but then it kind of, adds on, and it goes up here, and it gets a little higher, and you end up with something that does something like that. And basically you end up with, here in the middle, you can still kind of tell that these are two different things because you see this little peak in the middle. So let's say it was different distant car lights. For this guy, you might see, a car light and then a car light here. For this guy, what you're seeing is, I should have done those bigger, like a car light and a car light, and you can tell them apart. For this guy, you see like a car light and another car light, and they look like they're overlapping because they're so far away. I'm sure you've probably seen something like that. And then if they get either further away or closer together, I guess if it's car lights, the car gets, if the car is further away from you, what happens is you have, the first one, and then the second one ends up being really close to on top of it. Right? They're right there like this. And then the resultant you end up with, you can't tell it apart. You end up with some wavy thing, and then it looks like just an extra tall peak going like that, right? And then you can't tell the difference. They can't be seen apart, and what you end up seeing is something more like headlight and headlight right on top of each other, and you can't tell them apart. They look like one, one thing, because your eye can't spread them apart because their interferences are right on top of each other, and so they look like one thing. And I'm going to redraw this picture here a little better. So let's say we have our aperture, because I don't want to label after I already drew on that. Let's change that color. Go back to this. So let's say I've got this, and here's my aperture, my slit. We're going to call the width of that slit B. We're going to have two objects that are out here away from it, and they're equidistant on both sides. And then what we have is an angle to each of them like this. That was not very good. Let me try again. So an angle like that, not very good again, but a little better. And so this angle here is theta. We'll call it theta. And then we have the separation between the two objects. We'll call that x. And if you look at this, we also need to label this, all right, the further away thing. This is D. If you go through and you say that you use basically the idea that these two things are very far away, so so if we look at this, D is large, especially compared to x, so D is much, much bigger than x, and theta is small, which kind of is a consequence of each other. If D is much bigger than x, theta will be small. We can use a couple of little approximations. We can say that tan theta is approximately equal to sine theta, and since it's a small angle, sine of theta is equal to approximately theta. That's for D being really big and the angle being small. And if we do that, we can look at this. I'm going to draw it in here in light blue. We can say this is a triangle here, right here, this nice little right triangle. And we get that this angle is theta over 2. This is x over 2. And then, of course, this hypotenuse then is D. And we can write out then that theta over 2 is about equal to x over 2d, and then that gives us that theta is about equal to x over d. All right, and so we can figure out what theta is just basically from that, but you need a you need this kind of thing. Now, what gives you the best resolution? Well, this is going to be dependent upon wavelength, because wavelength and slit size will determine how much they diffract, right? The smaller the wavelength, the more they're going to diffract, and the further apart these things can be. We want a large aperture, so they're further apart, and then we get the less of that effect, and we get that. And then, of course, we also want a large theta. The further apart these things are, the more likely you are to be able to tell them apart. So in order to resolve something, you need, or your best if you have, so to resolve, your best situation is when you have a large theta, a large aperture, B, this aperture width here, all right, think like a camera, or your eye, right? You got that, and a small wavelength. The smaller the wavelength, the more you're going to be able to resolve them, especially compared to B. If they're off of each other, then they just kind of stay separated. You don't end up with as big of an interference pattern, okay? So we should be able to quantify this in some way, and it turns out we're not going to go through some kind of crazy derivation for this beyond the scope of what we need for this class, but we can use the result, and it's called Rayleigh's criterion. And basically, this is the most accepted value for a spherical aperture. Okay, for a spherical aperture, the most accepted value point where you'd end up with them just being resolved. In other words, it's the minimum that you need to get this. This situation was where they were just resolved. You could just tell that they were two separate objects, and this then is going to be the boundary for Rayleigh's criteria. Over here, this is unresolved. So anything above the angle for Rayleigh's criteria, or anything above Rayleigh's criteria, we're going to be resolved. Anything below it, we're not resolved. Okay? And we don't actually have to worry about D and X, because D and X together, they give us theta. So really, all we have to know is theta, because you can say, I have these two guys here, but if I move them here, well, then light coming off them is going to be exactly the same if I moved them closer. If I made D smaller, but also made them closer together, then all that matters is theta. And if they get further out, further away, but the angle stays the same, That's really what matters because the angle is based over x over d. That's why we showed you that. And so what we can do is just go ahead and give you his criteria, and it is that theta must be greater than 1.22 times the wavelength over your aperture width. Okay, that is the criteria for resolution. So to resolve two things into separate images and be able to make them out and tell that there's two different things there. This goes a long way in vision tests and things like that, where you're looking to see whether or not a person can look at one of those boards, that has an E and then some, A and G, and the letters go down and it gets smaller, smaller and smaller as you go down. And you're basically looking to see what you can resolve, and part of it is based on this, but it's also based on, of course, the focusing power of the little lens over your eye. But it also has to do with this criteria about whether or not you can tell, tell the two sides apart. So if I was looking at this H letter, and it was so far away that it was outside of this for my iris, then my human eye wouldn't be able to resolve it no matter how good my little lens was, and this H would just look like a blob to me. So like if I was trying to resolve the two vertical lines of the H, if it gets too far away, they'll just look like one little thing like that, and I won't be able to tell them apart. Okay, so that's what that's going for, and you can use this, to solve for what's the minimum wavelength you be able to see, and what's the aperture width you'd have to see to have it be able to resolve it. It's useful in things like microscopy, looking at things through microscopes and through vision and all that kind of stuff. Okay, then that brings us next to diffraction gratings. We're talking about resolving things up here with a single slit. Well, we also have to be able to resolve things in a diffraction grating, because one of the diffraction gratings jobs is to say, here's our diffraction grating, right? Let's say there's our diffraction grating, and we send in this light of all color, right? Light of all color, that's supposed to be white, and the white goes in, and then it spreads out. And when it diffracts, remember red and yellow and everything, so red's going to diffract like this and make these different modes. I guess the one in the middle too, and then red, and then orange is going to be right, next to it, and orange is going to diffract a different amount. That'll be right on top. So then this orange will go there, and it's going to red, orange, and then yellow is going to spread out from it. And dependent upon how far, we're basically trying to figure out is it actually able to spread out and resolve the different colors here, not resolve different objects, but rather or not we can actually see a separation of red and orange, let's say, whether or not they actually do separate out enough. And they'll separate a little bit, but is it enough that we can actually tell the red and orange apart? And so for that, we'll have this equation here. It's that R, called the resolvance, is equal to the wavelength over your change in wavelength. So if I'm trying to resolve two different wavelengths, say I had one that was like 390 nanometers and another that was like 390.45 nanometers, then lambda on top would just be 390. These have to be two wavelengths that are close together, so you put, it's basically 390. So you'd put that lambda is 390 nanometers, and then delta lambda would be the difference of the two of them, 0.45 nanometers, okay? You're not going to do this, you're not going to need to do this for something that's like 390 and 700 nanometers. They're not next to each other. So this is for two wavelengths that are close to each other. Really isn't going to make a big difference which of the two you put up there, because they're about the same. So you just put one of them up there. And then this can equal then M times capital N. So R is our resolvance, R-E-S, resolvance. This is about whether or not we can resolve it. Lambda is the wavelength, right? Wavelength, whichever one, they got to be close together, so just, either one's not going to make a difference. Delta lambda is the difference in the close wavelengths. And then M is what order, diffraction order you're looking at, right? Remember the M number that went with these, M, 1, 2, 3s and all that and stuff. So it's the diffraction order that you're looking at, because they may not be resolved in the first order, but they may be resolved in the second order or something like that. So diffraction order being observed. And then last is N. This is the number of lines of your diffraction grating, number of lines that must be illuminated. It's the number of lines in the grating, the diffraction grating, that's being illuminated. So if you look at something like this, you could say, all right, I need to separate out these two frequencies of light created by hydrogen. You know, it creates these two modes of light. I need to separate these two out from the diffraction pattern for hydrogen. And then I'm going, you can look at, all right, well, if I look at this order, and this is the difference in the wavelengths of the two photon types that are being emitted from it, the two wavelengths of light being emitted that are close together, how much of the grating will I have to illuminate in order to see a separation in that order? And then similarly, you could ask yourself, if I can illuminate this much of it and I have this, what order would I have to go to, and things like that. Okay, so this is our equation for resolving a diffraction grating. All right, I think that's pretty much everything for this section. Of course, make sure you've gone back and the other sections about diffraction gratings and about single slit diffraction before you understand all this stuff, and it should make more sense to you. Okay, but essentially this whole section is about these two right here. This resolves with a single. This is resolving two objects through a single spherical aperture, and this one is about the resolvence of a diffraction grating, about whether or not it can spread two similar wavelengths far enough apart that they will split and you can see them being split apart. Okay, that's going to do it.